Swayam Prabha. Digital India. Educated India.
So let us see why this cannot happen. So let's say that I have something in layer 10. I will not draw the earlier layers, but this is in L10 and this is vertex T, and just let's say for the sake, I don't know, this is whatever. So this is 9, 8, 7, 6. Okay, so there is a neighbor of neighbor X such that it is in layer 6. That is what we claimed, right? So then maybe it is a tree edge or it is a non-tree edge, right? But let us say if it was a tree edge, then T should have certainly been in layer 7, right? Now let us ask that this is a non-tree edge for sure, that is this X vertex lies here and this edge was not belonging to our tree. But what should have happened when we did this algorithm at X, when X was explored at this level 6, right? So what can you say about the status of this vertex T? Would it have been explored? I mean, already the tag should not have been given. The explored tag was not given. So it was unexplored when you were exploring the neighbors of X and you had the opportunity to explore it. That is, what did we do? For every V such that UV belongs to E, if V is unexplored, so T was unexplored at that time, you must have added it to T and also put it in layer Li plus 1, which should have been level 7, right? So therefore, such a scenario that you have a neighbor in a much higher level can never happen. So let us ask this question, that there are these tree edges that we have classified. What are the tree edges? The tree edges are exactly the edges that were added at this step into T. So every edge which gets added into the tree T, we will call it as a tree edge. Every edge that is left over, we will call it a non-tree edge, right? So one observation that we have already made about the BFS tree is that there are tree edges which certainly go from level I to level I plus 1. Are there tree edges which cross levels? No, because that is the design of the algorithm. We only have edges between the subsequent levels. There are non-tree edges certainly present in the graph. We have made one observation that non-tree edges cannot be from a layer I to a layer I minus 2 and above, right? That it cannot happen. So now let us ask, can there be an edge from, so an arbitrary layer I, this is Li, can there be, so this is there should be something in Li minus 1 because of which this vertex is in Li. So this is the tree edge. Can there be an edge to non-tree edge to a vertex in a layer Li minus 1? Can this even happen? Or even this is 4? This can happen very much, right? Because we can construct a simple example in which this can happen. Okay, so yeah, I'll come back to what she's saying, but I'll just complete this thought that we have. So one is, can you have edges which are non-tree edges which are between a layer I and a layer I minus 1, and that people seem to agree, and there is a simple example that you can have. So for example, if I had this graph, I would have put S, U1, U2, and then as I said, U3 may have been, U1 and U3 would have been explored first and they would have been put in layer 1, and then if this edge was there in the graph U3, U2, this would have been explored, but we would not have, would not have done anything because this vertex is already explored. So these edges can be there which are certainly, which can be present with respect to the layer numbering. What about edges inside a layer? Vertices inside a layer. Can they be present? Can they not be present? They will not be present. Okay, good. What is the reasoning? So can you give an example? So S is the first word. L minus 1. Okay, Li minus 1. And
U3 is present in
Li, okay. U1, U2 is an edge in the graph, right? Okay.
And
U1, U3, okay. Okay, good. But what I am asking is a generic question. This you are saying that at level 0 there will be one vertex, right? But in general I am asking, take any arbitrary layer and you look at the vertices, there can be multiple vertices. For example, in our figure we have so now let us look at this simple example. We have S, I'll just label this as U1, U2, and same thing that you were saying, U3. And now is it correct that this is the BFS exploration? S, U1 will be explored, U2 will be explored, and they will be put in layer 1, and then U3 will be explored, and so on. What about this edge U1, U2? This is present in the graph, and it will certainly be present, I mean that cannot be changed because you drew a BFS tree on the graph of the graph. So that edge is present, and when you explore U1, you must have explored the edge U1, U2 also in this process, but you saw that V is already explored. I mean V in the sense U2 is already explored, and therefore you do not add this as a tree edge, but this stays as a non-tree edge. Right? So these edges, that is edges between two vertices of the same layer, can also be present. Vertices, edges between two consecutive layers can be present as tree edges or non-tree edges. The edges between the vertices of the same layer are always non-tree edges. This is what we have identified. In addition, what we have identified already is that there cannot be edges which cross across layers. That is, you cannot have an edge from Li to Li minus 2, Li minus 3, and so on, right? Yeah, so these are the observations that we have made. So now, is this all, or are there some other edges that we need to consider? So the question that I am asking is, if you are given a graph, you have already classified tree edges which were added in this step of our algorithm here, and they have been labeled as tree edges. There are non-tree edges. We have said that non-tree edges can be of two types. One is, it can be between two vertices of the same layer. They can cross layers, but they can only be between Li and Li plus 1 or Li and Li minus 1 for any I. Right? This is what we have said. Can there be any other type of edges? Can we think of? Self loops, but we will assume that self loops are not present in the graph. So the graphs are, in fact, we will assume they are simple and loopless. Any other types of edges that are present in the graph? In fact, this is a characterization. That is, it says that all the edges in the graph can be characterized as either tree edges or non-tree edges. Tree edges are always between a layer and its subsequent layer, Li and Li plus 1 or Li and Li minus 1. And the non-tree edges are always present either between vertices of the same layer or they are present between two consecutive layers. Right? This is the observation that we have made. Okay, good. So now, and we have in fact proved this observation also, because we said that if this kind of if a non-tree edges crosses such layers, then our BFS exploration is incorrect, which cannot happen during our BFS exploration. Good. So now coming back to our, why did I ask this question? So when we gave L10 or 10 as the layer number for the vertex T, can we say something more about the path between S and T? We certainly have a path, and what is the length of the path in terms of the number of edges? Layer number, right? Because that is certainly a witness path. We have constructed that witness path. So we will also write one more observation, that is, if a vertex X belongs to Li in BFS of S, then there exists a path of length I from S to X. This is the claim, and this is quite obvious because we have constructed that path, we have shown that witness path. Now the question is, can there be a shorter path, can there be a longer path? Right? So let's try to answer both these questions. In typical, we would like to answer, can there be a shorter path than this, can there be a longer path than this? Okay, let's ask first, can there be a longer path than this, or this is the longest path that you could have ever found out between S and T? There can be very well longer paths, right? So you should try to construct an example which should be fairly easy, right? Now is there any confusion? You feel that there cannot be longer paths? Okay, sure. Now we can ask, can there be shorter paths in terms of number of edges? So we will say it a little more formally. So if there is a shorter path, that is, if there was a path of length j where j is less than I, then that path also has a witness that there is a path which is, let's call it, sorry, x is the ending, so s something something something, and the last vertex on this path, let's call it y and x, right? This is a path of length j where j is less than I. If this was the case, then what do you know about what can you say about how would this path look like in our BFS tree, right? So let's look at the first vertex on this path. Let's say S to U1. This U1 must have been put in layer 1 during our BFS exploration. Similarly, the vertex U2, if that is the next vertex on this, must have been put into layer 2, and in particular Y must have been put into layer J minus 1, and therefore X must have been put in layer J during the exploration. But we know that X has been put into layer I, which is strictly larger than J, which means that either our BFS exploration is incorrect or there is no such shorter path. Right? And these kind of arguments one can do a little more formally about doing it by induction on the number of levels, that is, at level I you have discovered the shortest paths from of all the shortest paths from S to vertices which are reachable via I length paths. You can do that induction, but this itself is an argument which tells you that there cannot exist shorter paths than whatever you have given as the layer number, right? And already we said that if you did not give a layer number to a vertex, then it is unreachable from that vertex in the graph, right? That is the only reason why you did not give a layer number. Okay, so I will just ask, so how long does it take to execute this algorithm? So we should ask how much resources are we using in terms of time and space. Okay, so let us do a little bit of formal analysis for this. So let us ask, how many times does a vertex get explored? At most once actually, because some vertices can never even be explored during the course of the algorithm, but every vertex gets explored at most once. Do you agree to this? Because you set a explode tag of false, and whenever you hit a vertex, you will explore it only if it was unexplored, right? So it is clear that you will explore a vertex at most once. So we should certainly count an order n. And why do I say order n? Because there are some other works that we do. We give a layer number to it, we set the explode tag of it. So in fact theta of n is okay, but I will give order of n of as the time that we spend in doing all this for exploring a vertex. Additionally, what do? Whenever we explore a vertex, we also explore the edges incident on it, right? So now you take a vertex, you explore the edges incident on it, and we do not know actually whether the endpoint was already explored or not, right? So therefore, in fact, when you go to U2, you will again explore the neighborhood. S also will be the edge U2S will also be considered during the exploration. So in fact, every edge will be explored exactly twice, right? If the endpoint of the other endpoint is unexplored, you will put it into the Q or the Li plus 1 layer. If it was already explored, you will do nothing, but you have certainly examined that edge. So you are just off by 2, that is, every edge is examined a constant number of times. Therefore your answer is correct, that is actually not only order m, it is order m plus n, because you certainly have to do n amount of work in terms of n in the sense, okay, the number of vertices in the connected component in S, right? So the number of vertices plus order m for exploring every edge once from its U endpoint, another time from its V endpoint, right? So this is the amount of work that this algorithm does in terms of the time required for this algorithm. Of course, there are other steps that we have not said, add something into the queue, pop it, DQ, NQ and so on, but each of these things are constant amount of work, so we are not writing down the running time because it's something into some n into some constant. Yeah, so now we have actually done one traversal. We have also seen some nice properties about the tree edges versus the non-tree edges of the graph. and what does BFS reveal about the tree edge or give in terms of the structure. In fact, there will be some very nice usages of this properties that we have seen in the tutorial questions that we have framed. So, you will be able to use these properties to do some interesting things about. So, we had listed some questions about what are special properties of the graph, and you may be able to answer some of them using these observations that we have made. So, in the rest of the time, we will try to quickly look at another traversal which is very interesting and which has a rich set of applications, which is the depth first search traversal of the tree. So, in contrast to what the breadth first search did, that is, it started at the source and tried to look at all the neighbors and then its neighbors and so on. The depth first, as its name suggests, is going to go deep down, and instead the analogy that we had about so many people are able to explore the graph or explore the neighborhood, is that you have one single person. You are the sole person who is exploring that graph. What you will possibly do is, if you find a route to go to somewhere, you will try out that route, you will go further and see, okay, can I reach T? Because I don't have that much manpower to spawn out so many people. So, I will just start at a vertex, keep going as deep as possible, but then I should not get lost, right? I should not keep going back on the same routes again and again. So, again I need some kind of a marker in terms of the explored vertices. I want to keep a tag that, okay, I have already explored this vertex, and if I come to this again, I should take a new route if I have not taken that, and if I don't find anything, I should go back along my path and see what is a possible unexplored vertex, right. So, this is the basic different strategy that DFS tries, and you may be aware that DFS is best written in terms of a recursive algorithm, and the contrast again between BFS and DFS is that BFS we used a queue to pull out the vertices in the layers. DFS actually implicitly uses a stack. When we do recursion, it is actually using a stack by itself. One can write it using the stack itself, but we will abstract it out and simply write a recursive program for DFS, right. So, again the same property, one of the similar properties that DFS allows us on undirected graphs is that it allows us to know what are the vertices which are reachable. The same information can either be obtained via BFS or DFS, but there is a different set of information or things that one can obtain using a depth first search, which we will start on undirected graphs and then move to directed graphs. So, in the spirit of BFS, we will also write a DFS, which is DFS exploration. So, here instead of just doing it starting at a vertex, I am just going to do a DFS exploration of G, and during this course it will explore a particular vertex, right. So, for all V, sorry. So, again I have this initialization of explored of V is equal to false, and if unexplored V, then I will call a procedure which is either called as usually visit or explore of V, right. So, this is the simple template of the whole algorithm, that is for every vertex. So, instead of doing it at a particular vertex, you can think of this explore as actually what we did for BFS, but we are just going to call it as explore, right. So, the first thing that explore does is explore of a vertex V. What should it do? It should set the flag explored as true, because this is the first time you are going to explore that vertex. So, I hope this usage of explore word is not too much. Explored of V is equal to true, and we are also going to give what is a timestamp. So, we are also going to give some numbers for every vertex. We will see why these numbers are useful in a later class, and these are called as pre-visit numbers and post-visit numbers. So, you think of every vertex getting two numbers with for every vertex. So, there are n vertices in the graph, then we are going to assign 2n numbers to the vertices, right. So, every vertex will get exactly two numbers and two distinct numbers. right? So think of a clock ticking. The clock has been set to 0 and or 1, and every time you give a number, the clock goes ahead, or the counter goes ahead, and you give a next number that is available, right? So I will say that pre-visit of V is equal to whatever is the counter, or I'll simply say pre-visit of V. So what does this pre-visit procedure do? It takes that global counter, it assigns that vertex the whatever is the counter number, and also increments that counter, right? So that is a global counter which is going on, and that is what pre-visit does. Now for each edge UV belonging to E, if not explored U, what should we do? Explore U, and when all of this is done, that is this for loop has ended, we will also call what is post visit of V. So what is post visit of V? It is again the same procedure. It will take that vertex V, it will give another number which we will call as the post visit number of that vertex, and it will give it from that counter and increment that counter, right? So every time you give a number to a vertex, that counter gets incremented. So in between some vertex, so you are doing pre-visit numbers, then you'll give a post-visit number. Every time you give a number to a vertex, you are going to increment that counter. And let us see an example so that we are clear what happens during our exploration. And we will see this on undirected graphs first, and then we will possibly move to directed graphs. Okay, so let us start our DFS exploration, and I will start it with a different color. So okay, so I start it at, let's say, S, and I explore this vertex. So what should I do? At this moment I should have done explode of S is equal to true, and I should have also given a pre-visit number. What is the pre-visit number? Initially, let's say the counter value is 1, so I have given a number of 1, right? As I go here, I will actually I will explore this vertex and give, let's call it U1, and I'll give a pre-visit number. And what will be the pre-visit number of this? 2, right? Till now I have not assigned any post-visit number because I am still here. What should I do further? I will now take a neighbor of this. Again, there is a choice whether I should have taken this neighbor or this one. Doesn't matter, I could have taken any one. So let's call this U3. I would have given a pre-visit number of 3. At this point, let us say we have explored this, and then you went to U4 and then gave a pre-visit number of 4. So now at this point what happens? So you are at U4, you are trying to look at, for every edge incident on U4, there is only one edge which is U4, U3, that is, it is already explored, so that you have nothing to do. So this for loop ends, and what do you now have to do? You have to give a post visit number, and this post visit number is going to be 5, right? Because this is where you have done. Now you come back to 3 because there is where the recursion will go back, and you will come back to U3, and then you will see that you want to again ask for each edge incident on U3. You would have already taken U3, U4 edge, and you will look at the other edge which is possibly U3, U1, and that is already explored, so you don't have anything to do. You are going to give a number which is, say, 6, and so on, right? So here, what will you do here? Will you give a number 7? No, in fact you will explore this and give the number 7 here, and then 8 here, and close this, and then you will go here and you will ask what should you do further. This edge will get explored in the DFS tree, and you will explore this. So everybody sees what is the pre-visit and the post-visit number. Is it okay? So you are giving 2 numbers to every vertex. Each of these two numbers are distinct, and these 2 numbers actually have a lot of information about the DFS traversal or the graph itself. It has a lot of information, and we will try to use this kind of information about or we will try to use these numberings to discover some nice properties about the graph. Okay, so just in the spirit of, so this numbering you can for now remember, and we will pull it back when we require it. So now, just as in the case of BFS exploration, there will be tree edges and there will be non-tree edges, right? So there is no layer numbering now, but you could also think of layers, right? So you can think of U1 being in layer 1, U2, U3 being in layer 2, U4 being in layer, and so on, I plus 1 layer. Now, is this claim true again, that if I find that U4 is in layer whatever 1, 2, 3, then it actually has a 3 length path from S? The path is there, clearly there is a 3 length path, because that is why I have, if I gave any layer numbers, but there can be even a shorter path, because there could have been, so I think I am in the red color, but yeah, so there could have been an edge which is of black color, which is between S and U4, which could have been there, and then there is just a one length path between S and U4. This could have been very well the case where you explored it like this, right? So if you find that, if you gave layer numbers, which typically DFS doesn't give, if you gave layer numbers, there is a path of length I, but there can be a shorter path than that, right? That is clear from this example. So we would like to ask ourselves that so in a similar spirit, I have not written the tree T, I am running short of time, but I hope you understand there is a tree implicitly, the red edges, and you can also write when to put an edge in the tree. And so there are tree edges and non-tree edges. We will again want to ask, how do the non-tree edges look like? In the case of BFS, we did a very clear classification that they lie between the same vertices of the same layer or between consecutive layers. Now, what can we say about the edges which are non-tree edges of this DFS tree? Right. So again, there are non-tree edges. So this black edge will actually become a non-tree edge, and there can be several non-tree edges. For example, this S and the unlabeled vertex U5, SU5 edge is going to be a non-tree edge. So is there some particular property that you would like to claim about the non-tree edges? And I would like you to think about, so now we have also used this intervals, you can think of these pre-visit and post-visit numbers as being an interval. That is, so what does this interval represent? It represents the, it represents that this vertex was active during this time, or alive, or was unexplored from this time to this time, this counter or whatever. Right. So I would like you to think about that if you have edges which are non-tree edges, you work out examples. Look at an edge which is a non-tree edge. Look at let's call that such edge xy. X itself has a pre-visit and a post-visit number. Y also has a pre-visit and a post-visit number. And based on this, can you say something about how do these pre-visit and post-visit numbers of X and Y look like if it is a tree edge, if it is a non-tree edge? I'll stop here about this exploration.